Hi guys, this is a video on worst case asymptotic analysis, in other words, big O analysis. First, let's define what this word analysis means in this context. In this context, analyze means examine some code or pseudocode and determine what its time efficiency would be. Time efficiency is an big O expression such as big O of 1, big O of n, or big O of n squared. An analysis is the result of doing this analysis process. So for example, I could say the introduction process I talked about in my earlier video on big O takes big O of n time. Analysis is a deep subject. There are whole huge books and courses on this. We can't get through all of that in this brief video. This video is going to go over the basics. But actually the basics cover most analyses. In practice, most of the kinds of data structure operations and practical algorithms you see can be analyzed using the methods in this brief video, and most of the deeper stuff handles trickier or more obscure situations. Ordinarily, we analyze for the worst case time of an operation. Worst case is the type of input that is the slowest. Remember that fast means a low amount of time, so slow means a high amount of time. So the worst case type of input would be the kind of input to an operation that takes the most steps. This is a careful way of doing our analysis. We're planning for the worst. So we're saying, here's this data structure operation. Maybe sometimes it runs fast, sometimes it runs slow. We're going to focus on the worst case scenario, the slowest it could ever be. This is consistent with the idea of under-committing and over-delivering. If I say that a given operation takes big O of n worst case time, for example, constructing an array and filling it, pre-filling it with default values, if that operation takes big O of n worst case time, I'm saying that even in the worst of circumstances, the slowest possible situation, it will get done in a linear amount of time, maybe faster. Maybe sometimes it's only big O of 1, meaning a constant amount of time. But if I say it's big O of n worst case time, I'm under-committing, over-delivering. Other developers will plan on this big O of n time, and if they plan their system around big O of n scalability, then the ultimate systems we build will work. Best case analysis, the alternative, that would be careless. So if I say an operation takes big O of n best case time, meaning sometimes it's big O of n, sometimes it's slower like big O of n squared, things could break because developers might plan their whole system around a scalability order of growth of linear big O of n, and when that unusual big O of n squared situation hits, then their system would be unscalable. It would be extremely slow, and people would be surprised by that. We don't want those kind of surprises. So now I'm going to go into how to do these basic analyses. Parts of an operation or algorithm take big O of 1 time, or constant time. If a line of code or pseudocode does no iteration, that line takes big O of 1 time. Iteration is the general term for any kind of repetition, such as a loop, recursion, or a function call that involves those things, loops or recursions. So most lines of code or pseudocode take big O of 1 time, constant time. Here are some examples. Initializing x to 0, I would say that takes constant time, big O of 1 time. Returning null pointer takes constant time because there's no loop or recursion or any other kind of repetition in that statement. Probably the other most common kind of operation in an analysis is a big O of n loop, a linear time loop. In general, if a loop iterates capital T times T for time, in the worst case, and it spends E time on each iteration, so T is the number of times the loop repeats in the worst case, the maximum number of repetitions, and E is the amount of time the loop takes on each of those, E for each, then the loop takes a total of big O of T times E worst case time. You know, you are repeating 10 times, each of those times you're doing E operations, you multiply those together, just like that class introduction example. So if a loop iterates n times in the worst case and spends constant time on each iteration, the loop takes big O of n times 1, which is big O of n worst case time. That's a pretty common kind of loop. You're probably accustomed to these very conventional kind of for loops. This one repeats n times and does a constant big O of 1 operation in the body of the loop, so that loop is a big O of n loop. Now, remember with loops that we're focusing on the worst case. So that's the maximum number of iterations. The phrasing on that previous slide was precise about the fact that we're saying if a loop iterates t times, in the worst case. So conventional loops like this one from the previous slide clearly iterate exactly n times. I starts at 0, we repeat as long as I is less than n, and increment I by 1 each iteration. This is one where it's not so clear because the loop might stop early. This is a loop that's searching for an element that is 0, so we have the conventional loop bounds, and if array element I is equal to 0, return true. Return immediately stops the function, so that will stop the whole loop, and could very likely stop the loop before I reaches n minus 1. If 0 is the third element in, then this loop will only repeat 3 times and then stop due to the return statement. So we wouldn't say this takes only 3 loop iterations, though, because we're analyzing for the worst case. So we assume the worst, which means the most amount of time, the most number of loop iterations. The worst case for this loop would be that it iterates all n times, because either there's no 0 at all and the loop finishes and we never return, or the 0 happens to be at the very last element of the array and we only find it at the end. So with a loop like this, we assume worst case that the loop repeats the maximum number of times it could. So most loops like this are big O of n time if they spend constant time inside the body of the loop. Now let's look at how you analyze a sequence of steps. A sequence of steps just means one step after another, not a single statement or a single for loop, but multiple steps executed one after another. The time complexity of a sequence of steps is equal to the bottleneck, and the bottleneck is the slowest of those steps, or the maximum time, the biggest number. So the worst case time of a sequence of steps is just the time of the bottleneck step. The bottleneck is the slowest one. Here's an example. This little snippet of code has 3 separate statements. There's the int declaration, the for loop, and the return statement. We analyze these separately using the rules I already introduced. Initializing result is a constant time step because there's no iteration. This for loop repeats n times and spends constant time per iteration, so that's big O of n. And the return statement has no iteration, that's constant time. So together we have 3 steps, a big O of 1, a big O of n, and a big O of 1. The bottleneck is the maximum of those, the slowest, which is the big O of n loop. That's where most of the time will be taken in this operation. So altogether, we say this whole thing takes big O of n time. That's because we're not worrying about the little +1 from the initialization and return statements. In terms of the amount of time this operation takes and how well it scales, the most important thing is the for loop. Those other steps take an insignificantly small amount of time by comparison. We really want to focus on the loop. That's what's slowing this down. So we call that the bottleneck, and that defines the time complexity of that operation. If statements use the same kind of reasoning. If an if statement's time depends on which branch gets executed. Here's an example. I've got an if statement. If x is 0, I spend constant time on assigning a variable, but if x is not 0, in the else case, we have a linear time big O of n loop. Sometimes when this runs, it will take constant time. Sometimes it will take linear time, big O of n time. The worst case analysis says you take the maximum of any of the branches. So in this example, in the x equals 0 case, it's big O of 1. In the other case, it's big O of n. We assume the worst and take the maximum of those two, big O of 1 and big O of n, which is big O of n. Finally, function calls. This is where your operation uses a different function or a different algorithm. If you're calling into a library function, such as those in the C++ standard library, the big O time bound is actually in that documentation. You may not have noticed it before if you weren't aware of this kind of terminology, but it's in there. C++.com has it, cppreference.com has it. In the description of all of the data structure operations, they say what the big O runtime is. If you are calling into a user-defined function that you created yourself or a teammate created, you have to do this analysis process yourself.